Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 7, Potential Energy and Energy Conservation Video 4. Today's topic is conservative force and potential energy. The objectives are to understand the relationship between conservative force and potential energy, to be able to apply the above relationship to solve problems. Let's see, finding conservative force from potential energy. For conservative forces, the work done by conservative force equals a negative change in potential energy. If we consider motion in one dimension, the force by conservative force, the work done by conservative force equals conservative force times the displacement, that equals a negative change in potential energy. We rearrange this equation, we have Fx equals a negative delta U divided by delta x. When delta x approaches to 0, Fx becomes negative of du dx. This is the derivative of potential energy relative to x. We'll find the force. This is a force from potential energy in one dimension. So if we know potential energy function, we can find corresponding force. So this equation shows that a conservative force acts to push the system toward a lower potential energy. That's how you go naturally. Object naturally falls downward. Spring naturally goes back to its equilibrium position. From this equation, we can also find potential energy. Potential energy equals to the integral of conservative force relative to dx, but it has a negative in front of it. So it's different from work because potential energy is negative work, right? Change in potential energy equals negative work. So it's negative Fx dx. Finding elastic force and gravity from potential energy. So those are the two conservative forces we have learned. Let's try to derive the forces from the potential energy equation. So for elastic, potential energy equation equals 1/2 kx squared. We derive it, do the negative derivation, we have negative kx. This says the elastic force on the spring and its displacement from the center position always have opposite direction. That makes sense. That's here is U. U is always positive, but when the spring is pushed, we'll try to unpush it, trying to move back to the original position. When the spring is pulled, again, it will try to go back to its original position. So when the x is positive, force is negative because it's trying to pulling it back. When the spring is compressed, the force is positive. Again, it's trying to go back. Now let's take a look at gravitational potential energy. If we know U equals mgy. So again, to find gravity, we do the negative derivative. You will have negative mg. This negative really means the direction. Direction is downward. That's what it means. So here is the graph. Potential energy decreases as y increases. So potential energy and y are directly related. And as a result, the Fy is negative mg. It's a constant, but below y is negative because it's going downward. Let's take a look at this example. An electrical charged particle is held at rest at a point x equals to 0, while a second particle with equal charge is free to move along the positive x-axis. The potential energy of the system is Ux equals to c over x, where c is a positive constant that depends on the magnitude of the charges. Derive an expression for the x component, force F acting on the movable charged particle as a function of its position. So F equals a negative dux over dx. What is u? U equals c over x. So c can come out. 1 over x is the same as x to the negative. So its derivative is negative x to the negative 2. So x to the negative 2 is 1 over x squared. So here, negative cancels, we get c over x squared. That is the expression for the force acting on the charged particle. Another example, an object of mass 0.5 kilogram experiences a force that is associated with the potential energy function ux equals 4 divided by 2 plus x, where u is in joules, x is in meters. Determine the force associated with the potential energy function given above. So force is a conservative force equals negative du dx. Okay, so that equals to negative. Again, for taking it out, so it's very similar to the last example. On the bottom is squared, but except you have to multiply by 1 because this is chain rule. Derivative of this over x is just 1. So negative and negative cancels. We have 4 divided by 2 plus x squared. Next question. Suppose the object is released from rest at origin. What is the speed of the particle at x equals 2? Since this is there is only conservative force, so total mechanical energy is constant. So u at 0 plus k at 0 equals to u at 2 meters plus k at 2 meters. U at 0, we simply substitute x equals to 0 into this expression. K at 0, we know is equals to 0 because you are released from rest. So here is 1/2 mv equals to 0. U at 2, we simply substitute x equals to 2 in that expression. And here is 1/2 mv squared. We have to find what v at 2 meters is. And so v in this case equals 2 meters per second. Another example, a 3-kilogram object is moving along the x-axis in a region where its potential energy as a function of x is given as ux equals to 4x squared, where u is in joules and x is in meters. When the object passes the point x equals to negative 0.5 meters, its velocity is 2 meters per second. All forces acting on the object are conservative. Calculate total mechanical energy. So total mechanical energy is potential plus kinetic. So let's see, what is the potential? Potential function is given to you, and we know at that point the velocity is that. So we simply substitute x equals to 0.50, substitute that for x, and velocity 2 as equals to mv squared. So that gives us 7 joules. Calculate x coordinate of any point at which the object has 0 kinetic energy. If an object has 0 kinetic energy, that means u has to be equals to 7. Right, from here we know 4x squared equals to 7, and we solve for x. X can be positive or negative, 1.32 meters. Calculate the magnitude of momentum at x equals to 0.6 meters. Momentum equals to mass times velocity. So we have to find momentum, we have to find velocity at x equals to 0.6. So we know u at 0.6 plus 1/2 mv squared. At any point, its energy equals to 7. So we simply substitute this expression with the known quantity. 4 times 0.6 plus 1/2 m times v squared equals to 7. We solve for v. Then we substitute this v into p equals mv to find p. So p momentum equals 5.78 kilograms times meter per second. Again, I'm using 3 sig figs. Last one, calculate acceleration. The magnitude, that means it has no direction. Well, acceleration equals net force over m. What is the net force? Net force in this case is the conservative force, and that equals negative du over dx. So we go back to ux equals to 4 times x squared. That derivative gives you negative 8x. So f at 0.6 equals to 8 times 0.6, which is negative 4.8 newtons. So acceleration should be negative, but that negative really indicates direction. The magnitude is the one quantity has no direction, so we just use 4.8 divided by 3. The magnitude of acceleration is 1.6 meters per second squared. Test your understanding, 7.4. So a particle moving along x-axis is acted on by conservative force Fx. At a certain point, the force is 0. Which of the following statement about value of potential energy function at that point is correct? Let's see, what do we know? How is force and potential energy related? Well, force equals a negative derivative. So when force equals to 0, that just tells us the derivative equals to 0. It doesn't really tell us the u value, except we know at that point ux is either at a maximum or minimum. We don't know. It could be 0, it could be greater than 0, it could be less than 0. So for this question, the answer is there is not enough information given to decide what is the value of u. Question B, which of the following statement about value of derivative ux at that point is correct? So we know f equals to 0 because it tells us that means the derivative has to be 0. So the answer is 1. That's it for today. Thanks for watching. See you next time.